Hi everyone, this is Mrs. Snowbeck. Today we are going to talk about Unit 9, Lesson 8. It's called Surface Area and Volume of Similar and Congruent Solids. So we're going to look at similar figures and we're going to figure out how do their surface areas compare, how do their volumes compare. And so remember, if you have two figures, like for instance here we have two cones that are similar, what does that mean? Well, it means they are the same shape, but they are different sizes. So if two objects are similar, they are the same shape, but they are different sizes. And then I want you to remember this, jot this down too. The ratios of corresponding lengths are congruent. Not the actual shapes, but the ratios of their different lengths. Next, let's talk about what it means if you have congruent figures. Well, if you have congruent figures, that means they are the same shape and they are the same size. So they're exactly the same. If two things are congruent, they're exactly the same. Let's make a little note. They have the same lateral areas, the same surface areas, the same volumes if they are congruent. And another thing to note is their scale factor. If two things are congruent, their scale factor is 1 to 1. Scale factor is how they compare. On your worksheet, it should say, state whether each pair of solids is similar, congruent, or neither. If the solids are similar, state the scale factor. So here's how we check. We take corresponding lengths, like for instance, this base edge and this base edge, and we divide those lengths. So 8 divided by 12, that can reduce to 2/3. Then take the heights. We can see this height here is 4, this height here is 6. Take those corresponding lengths and reduce. Also 2/3. Since the ratios of their corresponding lengths were the same, since we got the same answer for both of those, these are similar to each other. And the scale factor is going to be 2 to 3. You can write it as a fraction, or you could write it with a colon as well. Let's figure out, are these shapes, are they similar, congruent, or neither? So pick some corresponding sides. Like for instance, this 3 and this 1.7. Those are the front edges there on the base. Let's divide those. 3 divided by 1.7. And you get 1.76. Now let's take another length. So let's take the 6.2 and the 3.4. Those look like they match up. They correspond with each other. 6.2 divided by 3.4, 1.82. It is not the same. So I could stop right here and say these are not similar, they are not congruent, they are neither. If I wanted to, I could check the third heights here. Those would be corresponding. 2.5 divided by 1.5. That's 1.6 repeating. As you can see, none of these are similar, but all it really takes is one to be different. So my answer for these would be neither. How about these cones? Are they similar, congruent, or neither? Well, I can see they're not going to be congruent because they don't have the same measures on the radius or the slant height. But let's divide some of the numbers. Let's take the radii, for the 5 and the 6. If I divide 5 by 6, I can either leave it 5 over 6 because that is a reduced fraction, or I can type it in my calculator, 5 divided by 6, and I get 0.83 repeating, the 3 repeats. Now let's take the slant heights, the 12 and the 14.5. 12 divided by 14.4, excuse me. If I divide those in my calculator, I I get 0.83 and the 3 is repeating. Are these similar? Yes. They're not congruent, but they are similar to each other because their corresponding lengths had the same ratio. And the scale factor, there's two ways you could write it. You could say it's 0.83 repeating. You could say it's 0.83 repeating to 1. Or, this is kind of cool. You know how 0.83 repeating is equivalent to 5/6? So you could also write scale factor equals 5/6. So 0.83 repeating or 5/6, those are both good answers. I kind of like the 5/6 personally. The cubes at the right are similar solids with a scale factor of 3:2. Since these are cubes, the first one is going to be 3 by 3 by 3, and the second one's going to be 2 by 2 by 2. That's what it means if it's a cube. All the sides are squares, and they're all the same length. So next it says, find the surface area of each figure. Okay, let's find the surface area of the large cube. So remember, surface area for a cube or a prism is going to be pH plus 2b. P, perimeter of the base. Imagine the bottom being the base. We're going to add 3 plus 3 plus 3 plus 3, or 3 times 4. The perimeter of the base is 12. Next, we need the height, the h. This 3 on the side is the height. So 3 is the height. Then it's plus 2. And now think about base area. The base is the bottom and it's 3 by 3. So 3 times 3 is 9. So the surface area of the large cube, if we add that and simplify that, I think we get 36 plus 18, which is 54, and it would be centimeters squared for surface area. So there's the surface area of the large cube. Now let's do the smaller cube. So the surface area of the small cube. It's still going to use the same formula, pH plus 2b. Perimeter of the smaller base. So it's going to be 2 plus 2 plus 2 plus 2. You can see it outlined in red there. 2 times 4, in other words, is 8. Height. It's going to be on the side here. The height is 2. And then we have plus 2, and we need base area. Well, the bottom is the base, and it's 2 by 2, so that's 4. So we have 16 plus 8, which is 24 centimeters squared, and that's the surface area of the small cube. Awesome. Next, find the volume of each figure. All right. Well, let's think about this. Let's try to find the volume of the large cube. So for a cube, it's really a prism. We're going to use the formula area of the base times the height of the object. So think about the large one. Area of the base again, 3 by 3, which is 9. Height of the object, 3. Look up on the side there. 9 times 3 is 27, so the volume is 27 centimeters cubed. Remember, volumes have to have cubic units. All right, next, let's do the volume of the small cube. Still going to be area of the base times the height of the object. Area of the base, it's 2 by 2. 2 times 2 is 4. Height of the object, going up the side, is 2. 4 times 2 is 8, and we would label it centimeters cubed. So let's investigate a little bit more here. Let's compare. In other words, let's find the ratio of surface areas. The ratio between the large and small cubes' surface areas is 54 to 24. You can see those answers up there in the first part. Now, these can be simplified. 6 goes into both of them. 6 goes into 54 9 times. 6 goes into 24 4 times. So we can reduce that. 9 to 4 is the ratio between their surface areas. But think about these numbers. Both of them are perfect squares. 9 is the same as 3 squared. 4 is the same as 2 squared. I want you to remember that. We'll come back and talk about that in a second. Now let's look at the ratio of their volumes. How did their volumes compare? Well, the comparison was 27 to 8. These cannot be reduced. 27 and 8 don't reduce together. But think about the cubed root of 27. 3 times 3 times 3. 3 times 3 is 9, times 3 again is 27. 27 is the same as 3 cubed. Or in other words, the cubed root of 27 is 3. Let's think about 8. Think about 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. 8 is the same as 2 cubed. This is not a coincidence. Our original scale factor between the lengths of the objects, up at the top there, I just circled it in blue, was 3 to 2. That's the scale factor of the lengths. Now look at this. The scale factor, or I should say the ratio between the surface areas is 3 squared to 2 squared, and the ratio between the volumes is 3 cubed to 2 cubed. So the first one had an exponent of 1, the second one had exponents of 2, and the third one had exponents of 3. This is not a coincidence. This will happen every time when you compare similar figures. So here's the rule. It says if two similar solids have a scale factor of A to B, then their surface areas have a ratio of A squared to B squared, and their volumes have a ratio of A cubed to B cubed. Very important. This is the main idea of this section. Number 5. Two similar cones have radii of 10 millimeters and 15 millimeters. What is the ratio of the surface area of the small cone to the large cone? All right, we know the ratio of their lengths is 10 to 15. So I kind of like to do this. The ratio of the lengths is 10 to 15. Now, can that be reduced? Yes. 5 goes into both of them. 5 goes into 10 twice. 5 goes into 15 3 times. So 2 to 3 is actually the ratio of the lengths. So then in this problem, they want us to find out how do the surface areas compare? What is the ratio of the surface areas? So what we have to do for the surface area ratio is we have to take that 2 over 3 and we have to square them for surface area. So 2 squared is 4, 3 squared is 9. That is the ratio of the surface areas. That's your answer for part A. Part B, what's the ratio of their volumes? Well, for volume ratio, you're going to take that 2/3 again, but this time you cube the ratio. So that is 8 to 27. And that would be the ratio of the volumes of the small to the large. Now notice one other thing. They told us they want the ratio from small to large. That means we have to put the small one on top, the large one on bottom. Or if we do it with a colon, the small one first, the large one second. Order matters in this case. Notice we didn't find the actual surface areas. We're just saying what's the ratio between the surface areas. Number 6. Two similar cones have radii 9 inches and 12 inches. Part A, what's the ratio of surface areas of the small cone to the large cone? Okay, so think about how the lengths compare. The ratio of the lengths is 9 to 12. That's the radii. Can that be reduced? Yes, it can be reduced to 3/4. So really the ratio of the lengths is 3 to 4. So now think about the ratio of your surface areas. That's what we have to find. Well, you take that 3 to 4 and you square them. So it's 9 to 16. That's your answer for part A. That's how the surface areas would compare. Part B, what's the ratio of the volumes for the small cone to the large cone? So the volume ratio, again, take the lengths. The lengths ratio is 3 to 4. And this time for volumes, you cube that ratio. 3 cubed is 27. 4 cubed is 64. Now you might have to type that in your calculator. Remember, you use that caret button. You just use that. It's like an up arrow. And so if you do 4 raised to the third, you should get 64. 4 times 4 times 4, 3 times. Number 7. If the ratio of the surface areas of two shirts is 324 inches squared to 920 inches squared, what is the ratio of their volumes? Oh boy. This time they're kind of messing with us. They're telling us the ratio of the surface areas, and they want us to find the ratio of the volumes. Well, let's write down what we know. We know the ratio of the surface areas is 324 to 900. They want us to find the ratio of the volumes. Normally what we do is we take the ratio of the lengths and then we cube those, right? So we have to work backwards first and find the ratio of the lengths. So think of what we normally do. Normally we take the lengths ratio and we square them to get the surface area ratio. Well, to work backwards, you're going to have to square root them. So we're going to go back here and we're going to take the square root of 324 over the square root of 900. Now the square root of 324, feel free to use your calculator, it's 18. The square root of 900 is 30. Sweet. Can that be reduced? Yes, 6 goes into there. 6 goes into 18 3 times, 6 goes into 30 5 times. So the ratio of the lengths is 3 to 5. Now we can use that to find the ratio of the volumes. So take your 3 over 5 and think volume. You have to cube them. 3 cubed is 27. You can type that in your calculator, 3 raised to the third if you need to. And 5 cubed is 125. So that is our ratio of the volumes. Notice we didn't actually find the volumes, but we found the ratio between the volumes. Number 8, the softballs below are similar spheres. By the way, all spheres are similar. They're all perfectly round. If the radius of the larger softball is 1.9 inches, find the radius of the smaller softball. Okay, so think about it, you guys. The radius of this big one is 1.9, and they want us to find the radius of the second one. So there's lots of ways to do this one. Here's how I like to do it. We know the ratio of the volumes. The ratio of the volumes is 9.15 pi to 4.06 pi. Next, I like to simplify these as much as possible. And I see they both have a pi in them, so I'm going to cancel those out. So the ratio I'm going to work with for the ratio of the volumes is 9.15 to 4.06. This is going to be our ratio of the volumes. Now I want you to think about the ratio of the lengths. Okay, ratio of the lengths, we know the big radius. It's 1.9. We do not know the small radius, so let's just call that r. That's what we're going to try to solve for. Now these are sort of proportional, but we have to take into consideration how they compare to each other. Normally, what we have to do is we have to cube the ratio of the lengths to get the ratio of the volume. So here's what our proportion will look like. 1.9 cubed over r cubed should be equivalent to 9.15 over 4.06. We have to cube the ratio of the lengths to make them proportional to the ratio of the volumes. Now we can solve this. So we're going to cross multiply, just like we solved ratios a couple units ago. So you're going to have to type into your calculator 1.9 cubed times 4.06. When I did that, I got 27.85. That's equivalent to, if we cross multiply the other way, 9.15 r cubed. Next, think about solving an algebra problem. Divide by 9.15. Type it in your calculator. And I got 3.04. So 3.04 equals r cubed. And again, I'm leaving that number in my calculator. I'm not rounding it off in my calculator. I just keep building off of it. So now, to get rid of a cubed, you have to do a thing called a cubed root. And remember, to do this, you're going to have to take the cubed root. It looks like this. You're going to have to type in your calculators. If you have a TI-30, you're going to type in 3 second, and then it's like the xth root. It's above the caret button. It's above this caret button. And then you're going to type in 3.04 and then equals or enter. And when you do that, you should get approximately 1.45. So 1.45 is approximately your radius, and that would be inches. If that seems like a hard one for you, you might want to rewind and watch number 8 one more time. That's a pretty tricky one. Next, you guys are going to try Unit 9, Practice 8. I have a couple of hints for you on number 7 and number 8 of the worksheet. Number 7, some of it is in yards, and I think some of it is in feet. What I recommend is you convert everything to yards before you start calculating. And then number 8, use the scale factor to find the missing lengths in the small figure, and then use that to calculate the surface area of the small figure. So those are just a couple of hints. If you run into questions, let me know. Have a great day.